we will introduce the root function. Root. Last time we consider some limit laws, sum laws, difference law, product law, and quotient law. Finally, we have power law. Power means if some function f, the limit of this function when x approaches a exists, then the nth power of this function, the limit is the nth power of the limit. In other words, here n is a positive number. So suppose this limit exists. Inside the square bracket it exists. Then we take nth power of this function first, then take its limit equals, take limit first, then nth power. This is the power law. Power law. Once we have a power, we want to find some inverse operation of power. It is a root. Root. Oh. The power function, the power of a real number is denoted by this notation. Root. The n. Root of the real number a. This is the nth power of the number f of x. And this notation is read the nth root of the number a. Okay. If this is x, x, suppose consider the power function y equals x raised to the 1th power. This function has a property, different x, because the corresponding values are different. Such a function we call a one-to-one function. One-to-one function. If a function is one-to-one, I mean different. Numbers mapped by this function to different values. Okay, this one, if x1 is not equal to x2, then the corresponding values y1 is not equal to y2. A function having this property is called a one-to-one function. One-one function. One-one. If a function is one-one, then we can consider the inverse map. For example, here we given x1 we have y1, given x2 we have y2. Conversely, we may consider x also a function of y. X is also a function of y. For example, given y1, then to x1. y2 to x2. If these two numbers are same. This two numbers must be same. So we here in this notation, we consider y is a function of x. In fact, if we let y be the independent variable, then x is also a function of y. Here we will write x equals 1 through y. 1 through y. So this curve has two different names, but they are all the same object, the curve. One name is y equals x raised to the y-th power. Another name is x equals the 1th root of y. So we have an inverse operation. Okay. Consider this one. Y equals x squared. This function is not 1, 1 because some different values are mapped to same number. x1, x2. x1 and x2 are different, but the values of the square of x1 and the square of x2 are the same. Therefore, y, in this case, y is a function of x, but x is not a function of y. For example, if we given some y1 here, according to this rule, we will have two different values. Then this relation is not a function relation. But the inverse operation is very important, just like as long as we have learned addition, we must familiar with the subtraction. Multiplication. After multiplication, we need familiar with the division. Therefore, how to make this function become a one-to-one function? A very common way is to restrict its domain. Consider another function. Of course, the restriction may be here. X is not negative. Maybe negative, maybe some positive, some negative. Ask your wish, but usually we consider y equals x squared and x is greater than or equal to 0. Okay. In this case, now this function is different from this one because their domains are different. The domain of this function only consists of non-negative real numbers. Domain of this function is the entire real number line. So these two functions are different. This function has no inverse relation. Has inverse relation, but inverse relation is not a function. This function, if we have two different values here, different values. The corresponding values are also different again. Now, this function is a one-to-one function, 1-to-1. In this case, the inverse relation is also a function because if these two numbers are the same, this will be same. A function is nothing but a relation, preserves equality. Okay. I mean, if these two numbers are the same, this two numbers must be same, not like this. Here we have 1 equals y2, but x1 is different from, and x2 are the same. This relation is not a function relation. Okay. When we're talking about relation, we mean, suppose we have a set. A set is a concept, a collection of objects. For example, the set A has 3 members. The set B is also, okay, maybe also 3 members. A relation. Okay. Once we have a set A and B, we may consider their product. Their product is just choose one object from A and another object from B and put them together from a new object. This concept is very natural. It's very natural. Okay. Suppose A has 3 members, 1, 2, 3. B has 3 members, A. Okay, P, Q, and R. And according to this definition, the elements of this set is of the form and ordered pair. And the first component is chosen from A. If this component is 1, we have 1A, 1P, 1Q, 1R. If the first place is 2, we have 2P, 2Q, and 2R. If the first place is 3, the second place maybe P, maybe Q, maybe R. This is the definition of the product of 2 given sets. Okay. Once we have 2 sets, set A and set B, then their product is defined to be the set of all ordered pairs. And with the first component is an element of A. The second component is an element from B, of B. Okay, so we have some objects, another collection of objects, and then we choose each one from each. If some pairs have some relation, for example, 1 and P are correspond. A and 1 and P are related, and 2 and Q are also related, and 3 and P are related, for example. Then this is a relation between A and B, and this relation has a property that if if these 2 members are the same, then this is also same. So this is a relation has the property that this relation preserves equality. I mean, if A1 equals A2, then the corresponding number B1 equals B2. This relation is, such a relation is called a function from A to B. We may consider some other relations. Here, in this relation, we have if A1 is 1, A2 is 1, B1 is P, B2 is Q, then A1 equals A2 because 1 equals 1. And B1 is not equal to B2. So this relation doesn't preserve equality. Okay. So this relation is not a function. A function preserves equality. A function preserves equality. In fact, there are many possible relations. How many? Okay, this is also a function. This function not only preserves equality, because if these 2 points are the same, then this will be the same. Also preserves inequality. Preserves inequality. In fact, if these 2 are different, then these 2 must be different. But here, 2 and the 3 are different. 1 and the 3 are different, but the corresponding elements are the same. So this relation does not preserve inequality. Okay. A function preserves equality. Here, a relation preserves equality like this and this is called a function relation. So we have relations. From a set A to another set B. But a relation, suppose this relation preserves equality property. Then we have a function from A to B. Function from A to B. So functions are relations satisfies preserving the equality. Okay. From very beginning, set collection of some object, 2 sets. Okay. Relation between their elements. So we define the notion, this notation, ordered pairs. Then use this one, and then this relation can be denoted by maybe F equals 1P 2Q 3P. Well, so a function is also a set. See? Also a set. So in mathematics, all objects are sets. And this relation, maybe use this R, consists of 1P, 1Q, and 3R. Okay. This relation can be denoted by, for example, G equals 1P 2Q 3R. In fact, there are how many relations? There are 9 ordered pairs. Okay. 3 times 3, 9 ordered pairs. here, 3, 6, and 9. Maybe this one is chosen. Maybe not be an element of some given relation. So selected or not selected, just chosen or not chosen, chosen, not chosen. So 2 times 2 times 2 times 2. They are 2 raised to the 9th power. Such many relations. I mean, any relation, any possible relation. So mathematics consider things, not focus on some very special one, but it concerns the most general concept. Okay, they are there are 512 possibilities, relations, possible relations. This is only just one of them. One of them. In fact, this is maybe here, only one. This is also a relation from A to B. Also a relation from A to B. Okay. If no lines, then we say empty relation is also a relation. So there are 512 possible relations from A to B. Only some of them are functions, because relations, if they preserve equality, okay. So this is yes a function, and the domain of this function is only one element, one. So given the function which is a relation from R to R, we will consider its domain. Means f of x is defined. Yes. So gradually you will not just solve some even problems in test, in quiz, or in exam. Now you have gradually you should know what you have learned, the real thing, the truth, the real thing you should know behind. Okay. Functions. If a function, this relation already preserves a relation already preserves equality, also preserves inequality. Means if x1 and the x2 are different, then the corresponding values are also different. One-to-one functions or one-to-one relation. Okay. If a function is one-to-one, of course, we may consider reverse direction. Maps 1 to P, maps 2 to Q, maps 3 to R, then inverse. P is mapped by something to 1, 2, 3. The inverse relation is also a function. So we have inverse function. Here, yes, this is a function from R to R. And this one is also a function from R to R. In fact, the inverse function of this one. But this one, because this function is not a one-to-one function, so this function does not have an inverse. But this function is also one. The inverse of this function, x is also a function of y. We denote this one, the x equals the square root of y. So these two, this is the name of this curve. This is also a name of this curve. See, But usually people like customarily we would express independent variable by x. So, for example, this is 1, 1, this is 2, 4. If written y as a square root function of x, then we will have y equals the square root of x. 2, 4 here, then 4, 2 will be here. Okay, if we interchange x, now if we write the y, this is 4 as x, 2 x as y. In fact, this is the same function, but we use x as independent variable, y dependent variable. Okay. So of course, 2, 4, 2, 4, and 4, 2, 4, 2 will be 2, 4. I mean, to the right and to the above. Okay. 2 steps, then 4 steps. 2 right first, 4 second. If 2 here, then 4 here. You can see these 2 positions will are symmetric with respect to this line. With respect to this line. If 2 minus 4, right and below, okay. Below first, 4. Wait a minute. Right, above, and below, to the left. To the left, we obtain above is 2, minus 4. Again, these 2 points are symmetric with respect to the straight line y equals x. Okay? So interchange the coordinates of some point. It's just reflect this point or about this line to this position. Got it? Yes. 2, 4. 2, 4. Now 4, so to here. 2 here, so here. So just put this rectangle, rotate, similarly, rotate. Then the base will be height. The height will be base. According to this observation, we have, if we sketch the squared function, I mean the restricting squared function. The domains restrict to sorry. Yes. This is So these two functions, the graphs of these two functions, they symmetric it's a reflection about the straight line y equals x. Okay, so here, here, make a reflection about this one again itself. If we call this function f, then this is f inverse, or x-axis, y-axis, this is y equals f of x. And this is y equals f inverse x. Of course, same meaning. Same meaning. If y is a function of x, the name of the function is f. If this function is 1-to-1, then x is also a function of y. X equals f inverse of y. But here, the independent variable is y. If we express this one in terms of by x, then we obtain this one. Okay, suppose this function whose name is f. This one or this one? This one. This is a definition I just mentioned before. Here we, because this function is 1-to-1, so this function has an inverse. The inverse relation is denoted by this one.
What I mean is, why is it not x?
Oh, sorry. My mistake. Here, right? Sorry. Yes. Thanks. Yes. Okay. Because this function is 1-to-1, another name is x equals f inverse y. If we express the independent variable by x, then we have.
What I mean is, why is it not x is equal to y, not y?
These two are the same function, same.
I don't know.
If this is 1, the 1 power of 1 is 1. Conversely, the 1's root of 1 is also 1. Here, 2 squared, the 2 squared is 4. Then the square root of 4 will be 2. They are the same meaning if the x is negative. Later you will see maybe see more example. Okay, this is what x equals f inverse y. Means same f, but here y is independent variable, x is dependent variable. Here x is independent variable, y is dependent variable. So these two curves are symmetric with respect to this straight line. But usually, because some students, especially beginners, they will mix up. So we avoid use this notation. And also, 2 is so common, so we omit this number. And let's continue to powers for the powers are more than 2. This function already 1-to-1. So this function has an inverse function. We denote it by same. X is also a function of y. So the same curve has 2 names. Another name of this one is x equals y cubed. Okay, see. So now you realize here. Another name of this one is because it is 1-1. Another name of this one is but this is x, this is y, x equals y. The inverse equals itself. The inverse of this function, y equals x, the identity function is itself. Let's go further. Y equals the x to the 4th power. This is not a This function is not 1-to-1 because different values may be mapped to same value. So we consider its restriction. Now, this function is 1-to-1. The inverse of this function is denoted by so the corresponding root function is this is one way to call this curve. Another way is 4th. These 2 expressions are the same. Okay, they have the same meaning. Okay, finally, here, y equals x raised to the 1th power. Is first power is denoted by y equals x. We omit this one. Also, we omit this one because, but you have to know the true meaning of the inverse function. Here we omit the 2. When the root exponent is 2, we almost always omit this 2. And we almost never use this notation because this is 1. This is x. Okay, so if the power is an odd number, 1, 3, 5, 5 here. Then this kind of power functions are one-to-one. The inverse relation is denoted by, and the corresponding root function is okay. But for power functions, the power, the exponent is an even number. For example, 2 or 4, and the root function only defined for non-negative real numbers. Only defined for non-negative real numbers. Okay. Very good. So you already know the definitions of the root function. Okay. Nth root. Just the inverse operation of powers. In order to have a very convenient tool that we consider root function when the number, the exponent is an even number, only non-negative numbers are considered, are defined. But for odd exponents, 1, 3, or 5, and so on, yes, inside this root, inside this notation can be arbitrary real number, can be an arbitrary real number, positive, negative, or 0. Okay? I think it's time to write down the root law of limits. Okay, again, we assume this limit exists. Assume this limit exists, but when n is an even number, we have to assume this number is positive. Because if this number is a negative number, then when n is an even number, this number is undefined. This number is undefined. Also, we consider positive, not non-negative, because when n equals 0, maybe you will face to some okay. Consider the function to be the square root function, n equals 2. This is 0. Okay. For the square root, and at the position 0, this function is only defined on non-negative real. So this is correct. This is correct. Okay. Correct. And this one, because it is undefined, so this limit does not exist. Therefore, this limit also does not exist. So you cannot put this limit into. Does not exist, but this is 0. In order to this equality always true, we assume this one. Maybe at some occasion, some opportunity, maybe when this is 0 is possible, but sometimes equality does not hold. So for root law, not only assume this limit exists, but also assume it is possible when n is an even number. Okay, take a break.